Hey guys, today we're looking at angular momentum and a new conservation law. So, angular momentum is the rotational analog of linear momentum. We know linear momentum is P. Angular momentum, we're running out of letters here to use, so we're going to use capital L for angular momentum. So, basically, we know momentum is how difficult it would be to stop a moving object. So, angular momentum is how difficult it would be to stop a rotating object. And just like we've seen with most of our rotational terms, if we take a linear equation like P equals mv, we should be able to just replace each of these terms with their rotational analog. So the analog to linear momentum is L, or angular momentum. The analog to mass, which is a measure of an object's inertia, is just rotational inertia. And we replace linear velocity with angular velocity. So we see that on our equation sheet, that angular momentum is equal to I omega. But I have an interesting example here. If you are running and jumping onto a merry-go-round, there's an interesting thing that happens that I think we should visit, and that is if a child is running towards the merry-go-round and they jump onto the merry-go-round, we know that when they land on the merry-go-round, it makes the merry-go-round spin. So this merry-go-round acquires angular momentum that it didn't have before. So that would suggest that even this translating object of a child of mass m whose momentum is in this direction, somehow they had angular momentum. And somehow, if they were running towards the merry-go-round right towards the center axis, somehow when they land anywhere along this line, then no angular momentum is imparted on to the merry-go-round and it doesn't spin. So what I'd like to do is look at why this case of jumping and landing somewhere that's not headed towards the rotation axis versus landing anywhere along this line that is parallel to the rotation axis, why is there no angular momentum in that case? So if you take a look at your equation sheet, not only can angular momentum be measured with the angular velocity and I omega, it also says that we can calculate angular momentum of a translating object by doing momentum times the distance perpendicular to the pivot. So we've seen that before. We've seen R perpendicular before when we did torques. A torque is caused by a force with a component perpendicular to the distance to the pivot. For an object that's just rotating around an internal axis, where it's very simple to measure the moment of inertia and the angular velocity, then I would use I omega. But for that example of the child who's running, who's translating, they're just traveling in a straight line, it doesn't make sense to think about that as an angular velocity. But from the example shown, somehow there is a non-zero amount of angular momentum if the child is running in a direction that is not headed directly towards the center, or the kind of the forced pivot right there where the merry-go-round is forced to rotate around. Okay, so what I would like to do is use both of these equations in that specific example. So I have the child of mass m. They are running towards the merry-go-round with a speed of v, and they're going to jump on, they're going to land tangent to the circle. And of course, when they land, it's going to rotate. And what I'd like to do is use a conservation law to determine what is the angular speed of the merry-go-round when the child lands on it. Okay, so what I'm going to use here is the conservation of angular momentum. So the initial angular momentum is equal to the final angular momentum. So what would cause angular momentum not to be conserved? Angular momentum, as long as the sum of the external torques is zero, then angular momentum is conserved. Just like for linear momentum, as long as the sum of the external forces was zero, then linear momentum was conserved. In this particular case, I could also try to look at energy and linear momentum, and let's decide if those are conserved as well. So we have this child who runs and lands on a stationary merry-go-round. So the first thing I would say is if the child is moving and they land on the merry-go-round, there's no way that the relative velocity between their feet and the merry-go-round is zero, because the child's moving, the merry-go-round is not. And we know that if the relative velocity between surfaces is not zero when they touch, that there's going to be an amount of kinetic friction. And similar to a perfectly inelastic collision, if the child sticks to the merry-go-round, then there's no way that energy is going to be conserved here, because we have an amount of kinetic friction that's going to take mechanical energy and turn it into heat or thermal energy loss. For linear momentum, it's a little bit more difficult to see here. We know that the force that slows the child down is due to a kinetic friction between their feet and the floor of the merry-go-round. And the force that causes a torque that rotates the merry-go-round is just the third law pair to that. It's the kinetic friction between their feet and the floor that causes the merry-go-round to rotate. But the thing about momentum, anytime there's a fixed axis like this, if there is a fixed point that does not allow this object to move in a straight line, to translate, then we have to eliminate linear momentum. Any fixed point, when you pin something down and say, hey, you can only rotate, you can't translate, that's going to kill linear momentum. So really for this problem, the only thing that would be appropriate is angular momentum. But the challenge is determining what the angular momentum of the child is before they land on the merry-go-round, because they're really not rotating. But they have angular momentum because they're heading towards a point where they make a collision with the merry-go-round, and there is a part of the distance to the pivot that is perpendicular to their momentum. So their linear momentum would be exactly in the direction of the velocity. The actual distance to the pivot, we can see, I wasn't able to draw that very well. I should try that again. Sorry. It's hard to do, actually, to draw a long line that connects the center of the merry-go-round to the position of the child. So that's what we would call R. And as the child translates forward and gets closer to the merry-go-round, that R is changing. It's very dynamic. What's not changing is the part of R that's perpendicular to the momentum. The part of R that's perpendicular to the momentum is just one radius of the merry-go-round. So I would say that the amount of angular momentum that the child has as they approach the merry-go-round is just, again, P times R perp, and the linear momentum of the child is just mv. The perpendicular distance to the pivot is just one radius. And then the child sticks to the merry-go-round and they rotate together. So after the collision is over, since it's a rotating and a revolving object, I think it would make a lot more sense to just use I omega. So the moment of inertia of the merry-go-round, since it's kind of like a cylinder or a disc, is 1/2 mr squared, plus, since the child is now standing on the merry-go-round, they're a mass of little m, and they're revolving around that center. So they also contribute to the rotational inertia of the merry-go-round. So I would call that just an mr squared. So that is the total rotational inertia. And then I'm trying to determine the final angular velocity of the merry-go-round once the child lands on it. So if I want to get omega by itself, I'm just going to divide I to the other side, and I end up with mvr, which is the initial angular momentum, divided by 1/2 big M r squared plus little m r squared. So that's the total moment of inertia. And we have the angular velocity after the collision. Again, energy would not be okay because this is like a perfectly inelastic collision. We know there's got to be kinetic friction. And linear momentum's not okay because the merry-go-round is not able to translate. It's stuck to the ground, it's pinned. So we're always going to eliminate linear momentum in that case. The reason why angular momentum is okay, the exact force that slows down the child is also the exact same force, the third law pair, to the force that torques the merry-go-round. So since there are no external torques, there's no other forces that are causing the merry-go-round to speed up or slow down, it's just the interaction between the child and the merry-go-round that causes the child to slow down and the merry-go-round to start rotating. The sum of the external torques is zero. So we expect angular momentum to be conserved here. Okay? And I already made note about why it wasn't okay to use E or P here, but just to formalize that, just so we remember, anytime I do a problem now that we're in Unit 6, it could be a mixture of conservation laws. So back in the energy unit, you knew a free response question was going to ask about energy, but then we got to linear momentum, and sometimes it was asking about linear momentum. Other times we were looking at energy conservation. And now that we have so many tools in our toolbox, if we look at a rotational problem, we're going to have to consider all three of our conservation laws to determine which one's going to be appropriate. So for linear momentum, you know that you're looking for the sum of the external forces to be balanced, or no external net force. And the thing that's going to kill linear momentum is always a fixed point. If you have a fixed point, you're not going to use linear momentum. Energy, we're looking for any work done by external forces. So things like kinetic friction that are going to take away energy, that's going to mess up the mechanical energy. Work done by conservative forces, totally okay. When the force of gravity takes from your GPE pile and gives to your kinetic energy pile, that's okay. But if we have work done by so I should say instead of external here, non-conservative work. So any work done by non-conservative forces is going to mess with mechanical energy. And then angular momentum, as long as the sum of the torques external is zero, then we would expect angular momentum to be conserved. Okay? So every new problem that I face, I always go through my LEPs. I check, is angular momentum conserved? Is energy conserved? Is linear momentum conserved? And then I decide how I want to attack that problem. Okay? The other thing I want to look at real quick is angular impulse. If an impulse is a change in linear momentum, then an angular impulse would be a change in angular momentum. And we know how we calculate impulse from linear momentum, that is just force times time, or the area beneath a force versus time graph. So we could apply the same thing to angular impulse if I replace forces with torques, and I replace, well, time is a scalar, so I don't have to do anything to that. So torque times time would be an angular impulse, and that would determine the change in angular momentum on a particular object. Okay? So let's take a look at a quick example where I go through my LEP, I decide what is conserved, and eliminate any things that would not be conserved, and then I wouldn't use those to solve this type of problem. So you have something on a frictionless horizontal surface. It is sliding, and it's going to slam into this rod, and they're going to move away. It doesn't say they stick together, so I don't know if it's perfectly. I know that it's not perfectly inelastic. So they didn't say that they stick together. So there's a possibility that energy could be conserved. And it would only be conserved if they use that magic word, elastic. And I'm looking through this problem, and I don't see anywhere where it says that the collision is elastic. And if they're not specifying that it's elastic, then kinetic energy is not necessarily conserved. So since they leave it kind of vague like that, they don't say elastic, but they use the word here, must. Which of the following must be conserved? I'm going to eliminate kinetic energy here, because if they're not saying elastic, then there's a chance that kinetic energy would not be conserved. I mean, most likely, this is not an elastic collision. We know how rare and really uncommon those are. So linear momentum, angular momentum, we'll do a quick check. I don't see any fixed points. Nothing's holding this to the table. The thing that's going to make the rod move is the force from the disc. The thing that's going to make the disc slow down is the force from the rod. That's just an internal third law pair. So linear momentum would be okay. And then angular momentum, also okay here, because I don't see any external torques. When the ball hits the rod is going to rotate around its center of mass. But the reason why the rod rotates is due to the force of the disc. The disc is going to slow down and lose angular momentum because of the force of the rod on the disc. And since those are internal or third law pairs, I would expect the angular momentum to be conserved as well. So the two answer choices that I'm going with here are just A and B, linear and angular momentum, because the sum of the external torques and the sum of the external forces is zero. Okay? There is one other weird one that I think we should look at because I love this example. So I have that GIF there of the ice skater who pulls their arms in and suddenly they start to rotate faster, and then they spread their arms out and suddenly they're able to slow down. And if you watch any of the Winter Olympics, like those, I mean, those athletes are incredible and they have just a ton of talent. So this is a lot of fun to look at because it's hard to see what should be conserved here. And I've chosen this one in particular because they're just standing in the middle. They're not like in the middle of their routine where they're going around the ice. So I really don't even need to discuss linear momentum here because there is none. So the question is energy conserved? Is angular momentum conserved? And well, when I do energy, I always look for things like kinetic friction, external work, and it's not obvious to me. I don't see any. I don't see anything that would mess with energy. I don't see anything that would steal mechanical energy, assuming that we're saying that this is roughly frictionless here as they rotate on the ice. So I'm tempted to say that both energy and angular momentum are conserved because I don't see any external torques. I also don't see any non-conservative work. So, okay, then let's just move on. Let's say they're both conserved. But if you look at rotational kinetic energy, 1/2 I omega squared, and you look at L, which is I omega, how could these two be simultaneously conserved? That's the question that I have here. And there's nowhere to put the energy. Like, there's no potential energy here, there's no GPE. So, really, any change in I is coming directly from a change in omega, or any change in omega is coming directly from a change in I. So, if, for example, angular momentum was conserved, then it means that I and omega are changing inversely proportionally. So if I double I, then I have to cut the omega in half. And that's what's happening when I spread my arms out and they slow down. Okay. But if the moment of inertia and the angular velocity are changing proportionally, could I and omega squared also change proportionally? Well, if I is changing inversely proportionally to omega, it can't also change inversely proportionally to omega squared. So we have a problem here. And it turns out that our assumption about angular momentum is correct. There are absolutely no torques. There are no torques at all. There's nothing pushing on the skater to make them speed up. I mean, you can't really identify any additional forces other than the force of gravity and the normal force. So angular momentum has to be conserved. And if you were to measure the change in angular velocity, it's it's inversely proportional to the change in the inertia. So when they pull their arms in, their omega will increase proportionally. When they put their arms out, their omega will decrease proportionally. So why is energy not conserved here? Well, if you think about what's happening when they pull their arms in, right? Due to the centrifugal effect, their arms want to fly out. And I kind of think about like the frilly dresses that they wear and like the tassels that they might have on their uniforms. As they spin, we know that all those things they're gonna taper out, right? So, and that's because of the centrifugal effect. When you have a spinning object, the masses require a centripetal net force. So anything that's not strongly attached to the skater is going to move outward because of the centrifugal effect. And really everything. I mean, you see this guy's hair is spreading out because of the centrifugal effect. His arms want to do the same thing. So in order for you to pull your arms in, that is not an easy task. That requires some effort. And I would say that as they're pulling their arms in, they are actually doing work. That is not something that is happening naturally. They have to pull their arms in. Now, because that force pulling their arms in is directed towards the rotation axis, that is not a torque. Right? We know when a force has no component perpendicular to R, it's not a torque. But it does require work for them to pull their arms in. And then when they allow their arms to spread out, well, that's pretty easy for them. They just let their arms go, and because of the centrifugal effect, their arms spread out naturally. So that is work being done, which changes the mechanical energy. What I love about this question, though, is if you are getting a change in angular velocity, then it means you must have an angular acceleration. But we have said, according to Newton's second law, that I alpha is equal to the sum of the torques. I am claiming that the sum of the torques is zero, but I alpha is not zero. Now, what I love about this question is if you can get into the calculus of it. So right now, if you're in Calc AB or BC, you would actually know that Newton's second law is not equal to ma. So F net equals ma. That's nowhere in Newton's paper. What Newton actually said is that net force is the derivative of momentum with respect to time. And that means torque is not actually I alpha. Torque is the derivative of angular momentum with respect to time. Now, if you're not in calculus, that doesn't make a whole lot. Go ahead and skip to the next slide. But I love to look at that because really Newton's second law is not just ma. If you do the derivative of momentum and you do the product rule, you'll notice that there's also a part of Newton's second law that says velocity times dm dt. Now, what is dm dt? That's the rate at which a mass is changing. We don't see that very often. We don't see a mass changing until we get into like rocket science, where when you're burning fuel, the mass of the rocket is also decreasing. So we have this additional term to Newton's second law. Okay, that's great. We really don't get to see that at all in AP Physics 1. The reason why I bring this up, even though we don't have to do the calculus, if I now apply that same idea to torques and say that Newton's second law is not actually just I alpha, it is also omega times the rate of change of the moment of inertia. This is why I'm able to get an angular acceleration even without a torque. So I really love this problem. I love this example because the angular acceleration is exactly equal to minus omega di dt. So let's break this down. What does that mean? You're getting an angular acceleration not because of a torque. You're getting an angular acceleration because your moment of inertia changed. And that's what this equation is saying. They're saying if the moment of inertia is decreasing, then the angular velocity is going to go up. And if the moment of inertia is increasing, when you spread your arms out, then the angular velocity is going to go down. And I really love the simplicity of this equation. But again, it took a little bit of calculus to get here. I just want you to be aware of it because this is the type of thing that they do like to talk about on the AP exam, is this classic skater problem of letting your arms go, pulling your arms in. It's really important to note that angular momentum is conserved. Energy is not conserved because they have to do work when they pull their arms in. They're going against the centrifugal effect, and it takes a lot of effort to do that. Okay, so I hope that wasn't too much. I hope the calculus didn't scare you away. Maybe you want to take Physics C next year and you're excited about applying calculus to all the topics you learned in AP Physics 1. But for now, thanks for watching, and I hope I didn't scare you.